Oh, okay, sure. Hi, Professor Queloz. I'm today's host, Didier Queloz. Hey, nice to meet you. Oh,
hello, good morning.
Hey, good morning. Actually, it's a good afternoon in Beijing.
Oh, yeah, right. That's good afternoon for you.
So we started at 5 Chinese time.
Yeah, fine. Yeah.
Okay, we started roughly in 3 minutes.
No problem. Who is the cat?
Who is what?
Reza Zeng, the cat. I see a third person attending. It's a cat.
Oh, it's I don't know actually. Yeah. So, do you want to try your share your screen and see if it's working?
I will.
Oh, it's good. It's working.
What do you see?
Yeah, we can see.
Good.
All right. I think we can start at 5 Beijing time. So we still have more minutes. You can take.
You let me know.
Okay. So shall we start now? Are you ready?
I'm good to go. Shall we start?
All right. Let me start the introduction part. Although it's afternoon time in Beijing. So good afternoon, everyone. Welcome to today's lecture on exoplanet revolution. I'm the host of today's webinar, Didier Queloz from the US. We are honored to have Professor as our guest speaker today. Professor Queloz is a professor of physics and foundation in Cambridge University. Meanwhile, he's also the professor at the University. His research focuses on the exoplanet systems, the explanation of spectroscopy and transiting detecting terrestrial planets and life. And as you guys know, with home there in 1995, they discovered the 50 solar planets. Star 56. Since then, until now, more than 5,000 exoplanets have been discovered. For this discovery, he shared the 2019 Nobel Prize in Physics with Meyer and people. Today's webinar will address the challenges, the different models of planet formation, how to be also address the prevalence of life in the universe. If you guys have any questions, you may open your mic or write your questions in the chat and answer session. You may also click on your name that we shared in the chat box. All right, Professor Queloz, you can start your talk whenever you're ready. That's right.
Thank you. Shall I start? I can't hear you very well.
Yeah, you can start.
Okay, thank you. Well, thank you for this kind of invitation. So it's my pleasure to explain to you what I think is going on in astrophysics right now and called as a revolution with the many discoveries of planets orbiting other stars. And I will briefly give you an outlook where we're standing on that topic. But I will also show you where we are going to. I think it's a quite fascinating moment in the human history. We are not very far for understanding one of the biggest mystery ever is why do we have life on Earth and why do we have life in the universe? And I will explain to you what is the connections with exoplanets and these big questions of physics and chemistry and of the humankind. Well, let's start with the very beginning. We now have more than 5,000 planets that has been identified orbiting other stars. It means other sun. They are kind of all similar to our sun. What is interesting here is to understand that for almost all of them, we just don't see directly the planet. The reason why we don't see the planet is because the planet is next to a star, and the star is extremely bright. So we are blind, essentially, by the light from the star. And even right now, with the most powerful telescope in the world, we cannot easily see the planet. It will change in the future. There is new technology being developed, but presently, all what we have learned about planet is by indirectly guessing what is a planet about. And to show you what it looks, I mean, this is the technology that we have been using. It's very simple. When you have a planet orbiting the star, if you look at the star is moving a little bit. Because the system is globally orbiting the center of gravity of the system. And this tiny motion of the star can be detected. We can detect the motion in the sky, but we can also see the change of speed of the sky. And you see this kind of a change of speed that we measure by a change of wavelength, change of color that the light emitting the star is received by the telescope. It's called the Doppler shift. And depending where the star is going away from us or going towards us, you see the color changing, going to the blue to the red. So we've been using these techniques to find out planet. And if you're lucky at that very moment when the planet goes between the telescope and the star, you can have what's called a transit. It means for a brief moment, a fraction of the sun, of the stellar light, doesn't reach the telescope because the planet is acting like a shadow and remove a bit of this light. And this creates a little bit of a feature in the light we record, and we call that a transit. I'll come back on the transit. Now, these are the two techniques that we have been using so far in the last 30 years to detect planets. The physics is well known, it's from 19th century, and some of it is even Newtonian physics. There's no magic in terms of physics. Why it took so long to find planet? It's because it's technically difficult to build a machine that is detecting planet. The machine that needs to be built to measure the speed of the star needs a lot of new technology, and this technology was not available before the 19th. So my work 30 years ago was to make a new machine with a complete new technology. This is what it looks like, to measure the speed of the star within a range where we can find planets. How it works, there is three components which is critical on this machine. The first one is this big piece of optic that you see here, and it previews the high resolutions and the wavelength domain which is needed to compute the Doppler shift, which is very tiny related to the fact you have a planet orbiting the star. The second technology, you may see them, is this kind of orange-red fibers here, which are optical fibers. The optical fibers started to be on the market in the 80s. They were used by the telecommunication companies. But gradually it went into the visible light and started to be used in astronomy. In the 90s, we had optical fiber that could be used in astronomy. And for us, that was a major change because at that moment, we could remove the need to have the instrument sitting behind the back of the telescope and hanging around, suffering the change of temperature during the night. We could have the light that we pick from the telescope and brought the light down to the basement in a very stabilized environment. So we built what is known to be a stabilized spectrograph using these tricks of the fiber. The challenge here was to find a way to install the fiber, and the mounting of the fiber, this was a challenging development. And we were the first one to make, to be able to reach, I think, this new technology level. The third one is the amount of data you create is massive. And at that moment in the 90s, we had two choices to treat the data. Either you use a small computer, what's called a PC computer, but they were very poorly efficient and could not do serious computation. They were essentially used to do word, text, and bureautics. Or you go to the very big computer, but these big computers are usually sitting in the basement of big institutions or big university, and it was difficult for us to get access to it. But we got lucky because one of the big machine producers called the Cray Company had a couple of people leaving the company and created a startup company, which created this fantastic mini computer called the Sun Macrosystem. You may have heard about this system, using a new kit, which is called the Sparks computer. And they were much more powerful, immensely more powerful than the PC. And we could have it next to the lab. So I received this computer for my PhD, essentially, and I had to use this new kind of computer, super powerful, on my table to compute the data. All this together, we reached the fascinating capabilities to measure a speed of a star at a level of 10 meters per second. 10 meters per second is the speed of a running man. So it looks not very good, but considering that the motion of the Earth on its orbit is 100,000 kilometers per second, all the motion is huge in space. It's a very tiny detail compared to the big speed that you measure in space. Now, we developed this machine, and we were very excited because the effect of Jupiter, our own Jupiter, on our own sun is exactly at that level. It takes 11 years to see the whole orbit because Jupiter takes 11 years to go around the sun, but that was a level. And we started the program, and it was a big surprise to us to find out that actually we detected Jupiter as it was planned, but much faster than we were planning it, because the Jupiter we detected had only 4 days, a bit more than 4 days of orbit to go around its sun. It was completely unusual. It was a big shock. Most of the community didn't believe it. We had to wait a couple of more years until everybody was convinced that there were a lot of planets that are different from the solar system. So I want to just speak a little bit about this, and that's the best summary diagram we can use. When you have every dot on this diagram is a planet discovery, for which we have the period, the orbital period of the planet. That's what we have on the orbital axis, is the period in days. Pay attention, is a logarithmic scale. And we have two numbers we can measure. One of them is a mass, if you detect the Doppler shift. The other one, if you are lucky to find a transit, you detect the size of the planet. And you see three really blobs of planets. The one that belongs to the first discoveries, that what we call the hot Jupiter. They are the big planet of the mass of Jupiter, about that mass. Let me just flip this. Jupiter is here. And then we have the size of Jupiter here with the period. Pay attention at the period. It's a couple of days here. So they are very, very roasted Jupiter. It's a big mystery because we don't really understand how they ended up at these locations. We do have a lot of other Jupiter-like planets been detected, with most of them on shorter orbit, and also quite a significant number of them much more massive than Jupiter. It also was a big surprise. I mean, we have really big massive Jupiter, 5 times, 10 times the mass of Jupiter. But the most shocking discovery is this huge population of planets that are usually called super-Earth or mini-Neptune that have an orbit within days. Some of them are even shorter than 1 day, up to about 30 to 40 days, and the mass of Neptune. Now, the challenge of this diagram is it's an incomplete diagram. We don't detect all the planets we want because the technology we're using is limited in its precision to detect all of them. So I have to add this line, which is actually the limitation of the technology. So anything on the left can be detected. Anything on the right now, it's not possible to detect. And you do see something which is quite fascinating. I think you do recognize the Earth and Venus here, and they are on the wrong side of this diagram in the sense that we cannot detect an Earth and a Venus equivalent. We can detect an Earth mass, and we do have Earth mass, but they have to be on a shorter period. Or we can detect an Earth size, but again, they have to be on a short period. So it's a severe limitation right now, and in the sense that we cannot really compare how many of solar-like systems exist in the universe because we're just missing it. But the piece of luck in this diagram is nature has been nice with us because nature created a lot of planets that we can't detect. They are detectable by the technology right now. And the fascinating part of it is nobody had guessed they would exist. And when we do the statistics and trying to find out how likely it is, if I observe a star, that I find one of these planets, it's called the occurrence of a planet on a star, we ended up with this quite huge number. The hot Jupiter, the one extreme, they are a few percent, so they kind of rare events. The Jupiter alike, they're 10 to 20%, which is okay. But what is really amazing here, we have more than the majority of the star that have a planet within this domain. So the majority of the star you see at night, they have planets that are different from the planet of the solar system. And that is the main conclusions of 30 years of discovery of planet. Most of the stars have planets that are different from the one we have solar system. In a way, this is an extension of the Copernicus revolution we're living right now. 500 years ago, we said, well, the sun is the center, actually, not the Earth, and we have to rethink the way we're thinking of position in the universe. Later on, we find out a bit more than 100 years ago that we were in a galaxy, and there were many galaxies, and we were one amongst many. And now, at the last moment, the last chapter of this cosmologic, perspective, we're just learning that the solar system is not common, is not the vast majority of the structure of the planet in the universe. And that's quite interesting if you reflect on the fact that we are a planet in the solar system, the Earth, that is actually alive with life on it. So I'll come back on this element. So this is really the kind of a key message from the 30 years of discovery. The other key message is when you combine the mass and the size of the planet together, you build what is called the bulk density of a planet. And you can compare with known planets. If you compare with the Jupiter and Saturn, you realize that most of the hot Jupiter, they're a little bit above this, which means they're a bit lighter, which makes sense because there is a lot of energy which is beaming on this planet. There is a slight change of the structure of this planet. But Neptune clearly here cannot be explained by the structure of Jupiter and Saturn. If you see the Jupiter and Saturn structure, which is this kind of hatchet line we have here, Neptune is much denser because Neptune is a planet which is, in a sense, kind of similar to Jupiter and Saturn, but the big difference is there is no light gas, there is no hydrogen. So Neptune is quite often seen as a failed giant planet. So it created the momentum, the right mass at the center to accrete the amount of gas that is left over. But at the time Neptune reached this that level, I think no more gas was available for Neptune to trap and to grow. So that is the reason why Neptune has this mass and is setting below the density you would expect for Saturn and Jupiter. planet. But the good news is we have plenty of other Neptune that we're detecting on orbiting other stars. And this is all this kind of point you see here. There's a lot of planet that within the same mass range seems to be like Neptune. And to help to understand this very complex diagram, I included something as a reference, which is called a water planet. Why a water planet? Well, first, it doesn't exist, a planet only made of water. But the water is a very well-studied molecules, and it has been studied on extremely high pressure and extremely high temperature. When you make a planet, the internal part of the planet becomes extremely hot and very high pressure. So to compute a planet in a computer, you need to understand the physics of the material you're using. And water is well understood. So this is where would sit a planet which is made of water, which is a bit denser than the one of Neptune. That makes sense because Neptune has some light gas as well. Now, the fascinating bit, if you go down here in terms of radius, you get an even more compact object. You reach this green line. The green line is where you have a rocky planet. One Earth mass, one Earth size. This is where the Earth would be. And we do see that there are a substantial number of planets that do qualify with the term of rocky planet. So right now we have this immense diversity, which is much larger than what you have learned maybe at school about the planet of the solar system. Remember, in the planet of the solar system, there's only three categories. There is what we call the telluric planet, which is the one which are rocky, that goes from Mercury into Mars. Then you have the giant planet, that is Jupiter and Saturn. And then we have what we call the ice giant, which is Uranus and Neptune. So here we do see that there is more than three categories, actually. There is a continuum. There is a range, there is a slow change of the nature of the planet depending on the formation process. And again, this is a lesson number 2. It's called the diversity of the planetary system. So not only the structure of the planetary system in the universe is clearly different from the one of the solar system, also the structure of the planet can be way more diverse. And it opens a parametric space, which is huge right now, that we need to understand. What are these planets made of? What does it mean for the atmosphere of this planet? Can we understand why we have this rocky planet there? We have quite a substantial number of them, which is very massive. Like, let's see, this is 10 Earth mass here, right? So you have a 10 Earth mass, which is a rocky world, which is a super Earth, really clearly. But you could also have a 10 Earth mass, which is above this diagram, which is more like a fluffy, or maybe with a huge atmosphere, maybe 1,000 kilometer atmosphere of water. And then you can keep going up, and you have a Neptune, which is also 10 Earth mass. And you can keep going on, and you can have something which is like a kind of a small Saturn planet with a lot of gas, which is 10 Earth mass. So it's quite interesting. It's quite fascinating. It's quite also perturbing right now because we are a bit lost into this diagram. But the good news is we're making huge progress to understand what are these planets made of and how they can be compared with the solar system. We're using this trick called the transit. So just as a reminder, the transit is when the planet goes in front of the star, and essentially you are sitting between the star and the planet, and you detect this tiny change of light. So there is two moments which is interesting, which is being studied right now. The first one is when the planet is in front, it's called the transit, and the other one when the planet is behind, which is called the eclipse. You will see why the planet behind is a very interesting moment. We study this in many ways. I just mentioned 3 equipment that I'm familiar with and I will be using. The James Webb Space Telescope, you may have heard about it. This is space missions right now we're using to observe this system. The ground-based facility, there is a couple of gigantic telescopes on the ground being built up. They will be observing this moment. And there is future space missions. One of them is called Ariel, and they're likely to have more in the future that will observe this world. So I want to give you a bit of a glimpse. What does it mean, observing the system? What can we learn when we observe the system? And to do that, I have to do an experiment with you. I have to bring you into space and to take a picture with your cell phone. It's a picture which is in the visible light. So if you're flying in a space station, you take a picture. This is what you would get if you pick the right time with the moon. And this picture is fascinating. And I want for you to focus a little bit on some specific feature. The first picture I want you to notice is this tiny atmosphere, bluish, that we have on Earth. It's about 10 kilometers. So this tiny bluish atmosphere, it's blue because of the diffractions, the Rayleigh scattering that diffract the blue. This is why the sky is blue, essentially the most of the day. And that creates this kind of a pattern there. And this 10 kilometers is what we call the biosphere. So we are alive on this planet because or thanks to this 10 kilometers, very tiny 10 kilometers. Now, I will take the very same picture at the very same moment with another color using the infrared. The infrared is sensitive to the thermal emission of the surface of the planet. And if you pay attention to the area between the moon and the planet Earth, what you will see is the same picture, but without the atmosphere. You see, the atmosphere is gone. We don't see it because when you observe in the infrared regime, you see the surface of the planet, the thermal emissions. This is what the spy satellites are using to see what's going on the surface of the planet. Now, I will make another trick. I will observe with a very specific wavelength a bit further in the infrared, which is sensitive to a specific molecules that we all know and heard a lot about it, because this is making us alive on this planet. It's protecting us from skin cancer. It's called the ozone. It's an oxygen with 3 atoms, which is being created on the upper atmosphere by the high energy particle and emission from the sun and UV emission from the sun, and the oxygen, which is leaving the atmosphere. So it creates a very special molecule, which is unstable, by the way, on the upper atmosphere. This is very high, so I will take a picture sensitive to this very specific molecule. It means the light that we'll be using will be absorbed by the particle, and it will look like it's dark, and this is what's going on. And then if I do that right now at 9.6 micron, I see the size, I see the part of the upper atmosphere much higher up compared to the visible. I go back, this was before with the surface, and this is 9.6 microns. So this is 50 kilometers here. So what I show you is 50 kilometers. Now, the reason why I show you this 3 picture is to explain to you that the planet has a different size depending the color you observe it. Depending the color, you see a different size because you see a different height on the atmosphere of the planet. Now, when you do a transit, you observe exactly that. You observe directly the size of the planet. So if you do a transit measurements in different size, a different color, you will see different size depending on the atmosphere of the planet. And this is what is happening today. I show you one of these famous public data from the early light from the Webb Space Telescope. This is a transiting hot Jupiter. In that case, observed in different wavelengths. Every point is a size measurements. It's the amount of light which is being blocked by the planet, the amount of light from the sun being blocked. And you see there is up and down, up and down. And what's interesting, there is part of the wavelength when there is clearly the planet that looks bigger, this part, and at some moment, the planet looks smaller, bigger, smaller. Now, if you reverse that and you add an atmospheric model to explain this, you end up with this blue curve, which is the best model. And the reason this best model is interesting is because this model is essentially related to water. So if you add water into the atmosphere of this planet, it creates exactly this structure. It means the water will be sitting a bit above in the atmosphere, a bit similarly to the ozone, and you will be detecting this. Now, I hope I convince you right now by this very simple explanation that we can measure the atmosphere of a planet without seeing it. We just need to see the transit of a planet. And actually, we can do way more than that, because if you observe a system with a transit, you will have way more to detect with your telescope. If you have a telescope that we call the light, which is the diagram on the top, in this kind of system, you have this moment that we describe, which is a transit, when you have the planet that passed in front of the star. But you have this very specific moment when the planet is behind, which is what we said we would call an eclipse. Now, let's make a zoom and let's go down here. The time is going in that direction, so you have the time passing right in the system. So this moment with the secondary eclipse is very special, because remember, that is a moment when the planet is behind the star. It means you only see the star. You don't see the planet because the planet is hidden by the star. So if you think about that, it means that the light that comes to the star is about up to that point. Anything above is actually the planet. And you see this beautiful planetary phase function, that's how we call it. Depending when you look at the dark side of the planet, which is what we call the night, actually, you have less light, less night, less flux, less light from the planet. If you look at the day side, you will have much more light because it's either thermally it's hotter or it's reflected by the direct light from the sun. So you have this very fascinating shape here. And depending on this shape, is telling you the way the heat is distributed on the atmosphere. If there is an atmosphere, if there is no atmosphere, there will be a different shape here. And then you can imagine, you could observe that in different color. So you may see different species that have a different pattern. And if you have an extremely high spectroscopic resolutions, you may even be seeing the speed of the wind on the planet by using this technology. And this has been done. So you see that without really seeing the planet with the telescope, but just seeing this very specific moment of the transit, we can learn not only the mass and the size of the planet and the density, we can also compute the temperature of the planet, the wind speed, the composition of the atmosphere. And since we have some of them that are rocky, that it becomes very exciting, because then you can start asking, can we then study the atmosphere of rocky planet? And then next, does it mean that at some point we can study the effect of life on this planet? And that's what I would like to discuss right now with you, to explain to you how we can translate these capabilities that we do have. And this is not science fiction. This is going on. I have program, my colleagues are programmed, we're detecting this right now with the SAMS ground-based telescope, with space telescope, and it will be more and more in the news about this kind of discovery, and they will be even further in the future about doing more in these directions. But what does it mean? So to understand what it means, I have to take an example, which is the best example we have, a rocky planet, which is the Earth. So let's look back about the history of the Earth. So on the left side, you see what's called a clockwise history time sequence of the Earth, starting on the bottom here and going around until you come back here. So at the beginning, you start, it's very hard. You assemble the piece of the planet, you release and you lose a lot of the light gas like hydrogen and helium. There's a lot of material falling on the planet, bringing essentially carbon, CO2. We have a massive impact that is creating the moon. So it's called the Theia impact. It's a massive body that hits the Earth and take out part of the material of the Earth. And then the leftover is rebuilding the moon about 20 million years after the formation of the solar system. And gradually, within a couple of 200 million years, the Earth is cooling down. There is a settling of the material. The very heavy material are sinking into the core, initiating the magnetic field. At some point, the plate tectonics should start here, dragging the cycling of the CO2. And then there is a moment called the prebiotic when you start having life. And we have no traces of early life. Only about 500 million years after the formation of the Earth. And there is a slow period where not much is visible, and then you have this rise of oxygen. And the whole atmosphere is completely changed. It is so much changed that anything you're breathing right now, any oxygen, has been produced by living organisms. Even the carbon that we're using has been reprocessed by living organisms. This is why we use the carbon-14 as a trick to find out how old it is. So the whole Earth system has been completely populated by life, and life has transformed the whole structure of the atmosphere into living into a kind of a very nice balance until recently, because now we're messing up this balance in a serious way. So the reason why I want to mention this here is, as an astrophysicist, this history can be translated into observations. What do I observe? Well, I simply observe the atmosphere of the planet. And depending the time when you observe the planet, and the location of this on the time scale, I would have a complete different signal. And you have on the right simulations of the signal, the spectroscopic signal with the ups and troughs. You can see that as the size of a planet in a way if you observe with the transit, similarly than what I described. And you do see that the structure of the signal is very different. We're not talking about a small difference. We're talking about a huge difference, depending if you look at the Earth before there is life. It's called the Archean Earth. At the beginning of life, which is the Proterozoic Earth, or in the modern Earth. So essentially, by observing atmosphere of a planet, we can say something about the geophysical evolution of the planet and, of course, the impact about life. So technically, we can look for life by looking at the feature into atmosphere, feature that is left over by life. So this is a moment where we are, and it's quite a fascinating moment into human history. So to open this last chapter, I would like to mention, I think, a very nice vision. It's almost a philosophical statement from a famous astrophysicist, which is Christian de Dieu, this Nobel Prize astrophysicist, who got fascinating at the end of his career about this idea of life in the universe, and got convinced that there is nothing magic with life. It's just part of physics. I think, in a way, when you create the universe, the law of physics are set, and the law of physics enable life as well. And he's even been pushing it a bit further. And he said, well, it's not only life which is embedded into the universe. It's also the concept of intelligence, which we would refer right now in terms of consciousness. Now, our brain, everything we have, operates into this universe. So in a way, we are part of it. So we should be able to find a pathway to understand how it works. I think it's amazing, this statement. And if I bring this into astrophysics context, essentially what Christian de Dieu is telling us is there is a link between all of this. At the beginning, you create the universe, essentially, and the universe creates time, space, and matter. Most of the matter, we don't really know what it is. It's called dark matter. And other matters at that moment being created is essentially, the visible one is essentially hydrogen. There is a lot of neutrinos on this, but essentially the hydrogen is the most visible with the atoms, the most visible part of it. The hydrogen is a bit of a boring material, and nothing much would happen in the universe. So it would be a very boring universe if only this would be available. But the law of physics was such that the hydrogen can react and can assemble and create stars. And the star is a kind of a fantastic machinery that would then produce a lot of chemistry, all the wood chemistry, a lot of chemicals, stable atoms into the Mendeleev tables. And on that reason, the star is kind of a new, fresh chapter into the history of the universe. And the star is not magical. In a way, the law of physics that enabled the star to function and to create all these elements of the supernova was already there at the beginning. So the star does not only do that, the star also, the leftover from the star, is creating the planet. If you only have stars and no planet, well, you will have a very poor chemistry, because you have a chemistry called chemistry in the universe, so you don't create this kind of a diversity of chemistry. So the law of physics, again, was such at the beginning that it would enable the formations of planet as well. And the planet is becoming lab. Really, essentially, they are labs. They're labs, they're chemistry labs, because they're all different. They all have different mechanisms. They all have different temperature, different compositions, but they are doing chemistry. They're doing chemistry in a more complex way. And some of these planets are so efficient at making chemistry that they are producing the chemistry of life. And then here we are. So essentially, the story I'm telling you is, from the very beginning, you have into the law of physics the functioning of life. The question is, how do you end up there? And you can even push further and mention that our own mind, our own brain is just following the law of physics. And it was already there. The potential of creating this was there. Now, what we don't really know is how likely it is, and how much frequent it is, and how long it will last. So we know that the typical timescale of the mean that life that happened on Earth also happened on Mars and also happened on Venus. Well, clearly Venus is unlikely to have a life right now because there is no more recycling of CO2 and it's extremely hot and it's full of cyanuric acid. Well, some people may claim that there is still possibility of life maybe floating around. Mars, there is water. We know there is nothing on the surface because the atmosphere is gone. Mars lost the atmosphere, possibly inside. And when we will be exploring Mars in full detail, there will be some findings, possibly, but I'll come back on Mars. But right now, there is no clear evidence at this moment. But what can we say about life? So here the challenge is huge because we are in a situation where we only know one life, and we only know the life that we are experiencing ourselves. So if I go to meet my colleagues biologists and I talk about life, they tend to believe, oh, life is so exceptional, so it is unique in the universe. And there's good reason to see that because the way that the biologists see life is this. It is a functioning of life as it is right now going on Earth. It's a very well understood mechanism. It's a very well balanced system. It's like a Swiss watch, and it seems magical. Of course, it's a result of a couple of billion years of evolutions. And this is what right now is going on in your body. Your body is doing that at every moment. And this is why this is being kept alive. And pay attention that it's not only your body, it's even the trees outside. They are functioning with the same basic mechanism. So this is a challenge, and the practicality is difficult to understand this because it's so complicated. It's like looking at the computer and trying to understand, how do you start with the first computer? It's exactly the same problem here. So people tend to simplify and tend to look at things, and they say, well, there is different kind of life, the eukaryote and prokaryote, and who comes first and how do they evolve? And you can at some point study that, but it's a very specific development of life. Nothing is giving you any hint that you would do exactly the same if you would restart. So it's not very clear. So you have to go backwards and try to think in a more conceptual way, and you end up with a function of life. So we can in fact agree there is at least 3 functions of life which seems to be absolutely necessary to make life functioning. Well, it has to replicate, so you have to find the tricks to replicate. We're using now the RNA as a key mechanism there, and the DNA. Well, is it the only way to do that? Is this the most optimal way to do that? We don't really know. You need to find energy. So chemistry is about dealing with energy. You need either to bring some heat, a UV flux, or in the case of the life, there's a tricks where they degrade the level of electronic, the electrons, in a way to enable the chemistry to happen. It's kind of a trick here to play with the chemistry, to make this chemistry, this machinery creating the energy. And of course, you have to be careful you not dilute into space. So you have to get some membrane, something that protects you, but the membrane should be good enough that it's not completely isolating you from the outside. Otherwise, you don't get nutriment into your living organism. So we kind of agree with these 3 functions. Now, how they started and whether there is an order, it's not very clear. There's a couple of common ground here, and there is foundations. We understand there is some chemistry which is similar, and in a way, they should give us some clue. But the function itself is difficult to use by itself. Now, the big problem we're having right now is we have this immense view of life as it is on Earth, and we're also going back to what's called the tree of life. The challenge here is the time scale. So to try to share this concept with you, this is the tree of life I like showing because it shows the diversity of life, which is essentially the time diversity of life. So today is the outside of this diagram. So you go from the bacteria until us, which is the last bit in the human on the far right of this diagram. So the outskirt, the surface of this diagram is the tree of life as we see it today. Now we know we can go back and you see there is clearly dividing line here, and you see the evolution. At some point there is a common history here, which is related to the early birth of life. But in terms of time scale, it's almost 4 billion years ago. Now, the challenge here is how far can we use life as we know it today to find out how life was at the beginning? And Unfortunately, I think we can't. I think there is a kind of a wall of fire here that protects us, that prevents us to see what is going on really at the beginning. So far, going backwards, we reached some key points, certainly some early phases, but then the only way to get the early birth is trying to go in the reverse way. So what people are trying to do right now is they're trying to connect these two together. They're trying to bring the history of life backwards as much as we can, and then there is clearly a limit here. But we're trying to go onwards, start to create life into lab, and to move upwards to understand how we connect to life as it is. Now, there is a couple of elements that we have to help us here in this process. The first one is to realize that right now on Earth, given the condition that we have experienced, we have never detected life being made from zero. But the only thing we've seen is life being replicated. So we own replications. We own replication in previous life, and that is a replication in previous life. But there is no life being created from scratch right now on Earth. And that's quite of an interesting feature to realize. I mean, there's a famous Pasteur experiment when he's taking two boxes, and one of the boxes is just sealing the box. There is nothing. It's just sealing the box and leave it aside. And the other one is sealing the box, but also bringing on the high temperature to kill every germ and everything. And he demonstrated that a couple of weeks later, the box that was empty, theoretically, has been sealed, but not sterilized. Well, there's plenty of life in it. And the other one that was sterilized has no life in it. That was to demonstrate actually life was already there in the air. We don't see it because it's microscopic, but it was already there. So we just kept replicating it. The other one that there were no life because they killed any life, there is no life developing into the other box. So I think the idea of making life from scratch is something that people is a bit obsessed right now, but they have not found any evidence of location on Earth where life is happening from scratch. And there is good reason for that, because I think the moment when life happened was very different from it is right now. And I tried to give you a little bit of a picture how Earth was if you go back in time of about 4 billion years. This is what it is. It was a very different Earth because the level of impact, the level of volcanic activity, the kind of atmosphere you're talking about was completely different. And if you want to understand the origin of life, you have to consider this is the cradle of life on Earth. And this is not what we have right now. So the challenge right now is using the best knowledge we can in terms of chemistry and biochemistry to find out whether it can make sense. So the other hope here is how far can we find and trace back something from that moment. And here we have a problem. We have a problem which is in a way related to the fact we are alive, is we have the plate tectonics. The plate tectonics is crucial to recycle the CO2, otherwise it will build up the CO2 and end up like Venus. So it brings the CO2, you write down the CO2 into the oceans, bring it down and recycle completely, will process it. Well, by doing that, of course, it also will process anything on the surface. So anything you left on the surface of the planet, whatever it is, after some time will be recycled and brought back into the crust, into the mantle of the Earth. There are few rocks that manage to survive, but essentially the way you have to think about that, they manage to float like a boat on the surface of the Earth and never, when recycled, into the mantle and diluted. And they're known to be zircons, and they're very early on, very, very ancient. But there's still a hope that there may be a piece of rocks, very old, that people is going to find out. And I know my colleague scientists are still dreaming about this, where they could imprint what happened with life at the very, very, very moment. Unfortunately, it has not been found and may never be found because of the reason I was mentioning here. So to understand the origin of life at that moment, what we have to do is we have to relate to lab experiment. We have to make it. So what do we know about making life into labs right now? So there is 3 competing theory, and the size of the likelihood of the theory, is according to the size here of the diagram. The most unlikely process is what people usually as refer to the origin of life at the beginning of the oceans, beginning black smokers or dark cities, this kind of smokers you have on the bottom of the oceans. There is a huge issue with this theory. The first one, there is no chemistry theory. The second one is dilution. So there is, when you create life, you should not dilute, you should concentrate. Because if you dilute, you just lose, I think, the impact to build and flourish life. And the third big problem is if it's so efficient, it should be still making life today. And this is not working. So it's unlikely to be the origin of life. As a chemistry process here. So there's this famous experiment from the late 60s, 70s, which is the Miller-Urey experiment, which is very fascinating because they explore the possibility for life to be starting on the surface of the planet using a very special atmosphere. Actually, it was a methane, ammonia atmosphere with electric discharge, so a lot of energy there. So it's a very energized atmosphere. It's called reduced in chemistry, highly reduced chemistry, and also very extreme environment. So certainly some of the environment is valid. I mean, the lightning is certainly valid. But what we know was not valid is the fact the atmosphere is highly energized, and you could not sustain an atmosphere of ammonia and methane. So the reason is very simple, because there's so much energy into this gas, so the gas will naturally degrade, and you will lose this atmosphere. So you need to replenish, you need to rebuild the methanes and the ammonia every time. Otherwise, it's going to dilute. It will be diluting and reacting, becoming neutral again. So it's still an interesting scenario because due to the high impact of comet, we know that cometary impact can trigger such a chemistry, and we have satellites of some of the giant planets of the solar system, Titan and Enceladus, that may experience such a kind of a chemistry. So it's a very fascinating chemistry. It may be related to some kickstarting of life. I don't think it is likely to be the origin of life on Earth, but it's a very worth to be studied chemistry, especially by exploring a satellite of a giant planet of the solar system, because we can do that, and this is going to happen. The next challenge for the next 50 to 100 years of space aeronautics will be to really go to explore these farther worlds, and this is starting, but I hope there will be more in the future. Now, the most common scenario right now that people tend to agree on is what's called the cyanosulfidic chemistry, simply the HCN. HCN is a deadly gas. You don't want to just play with that, you will die. But this is extremely rich in terms of chemistry potential. And it can happen, you create easily HCN on the comet, so it's easy to have HCN on the planet. The idea here is the chemistry is happening on the surface of the planet, into pond, into lake, into rivers, and you use the UV flux on the star as a trigger for the chemistry. A couple of experimental paper has been published in the last now 6 to 7 years on this theory, and this is gaining more and more momentum, with serious progress being made to consider the formation of the amino acids. This creates very easily the 20 amino acids that life is using. Some of the nucleotides as well being produced, and even some of these membrane molecules called lipids molecules that is related to life. So there is a possibility that this scenario is going to lead us tomorrow into a lab to somebody claiming that they have created the key ingredient for life and they are assembling together into a kind of a proto-life mechanism that have the three functions that I was mentioning before. So the reason why it's fascinating, this theory, is because there is a series of specific predicted conditions for life to happen. You need to understand the geochemistry of the surface of the planet, and of course you need to understand the geochemistry of the atmosphere of the planet. Now this is where astronomy comes, because the geochemistry of an atmosphere of a planet, this is something we can measure. We can measure by detecting the spectra or the surface feature of the atmosphere. So technically, we can test some of the assumption which is being made by this chemistry on the planet, and the chemist on the surface of Earth can test in the lab to see whether with these conditions observed in the planet, they can make the origin of life. So you see this kind of connection which is starting to build up, where we are addressing the questions of the formation of life and the chemistry of making life, and also the condition the geophysical condition for which you need life to be met to happen. Now, we are also doing a very fascinating experiment that I want to mention that will keep going, is this exploration of Mars. So Mars is a quite interesting planet in the sense that we know that the first billion years of Mars was full of water, and possibly with oceans and lake. It is even possible that at that moment, if you would take a picture of the solar system, you would end up with 3 planets with water and maybe looking at kind of bluish, which is Venus, Earth, and Mars. And Venus went a different pathway and lost completely the water and ended up with a fully greenhouse terminal effect. And Mars, because of the smaller mass, lost the atmosphere and gradually. And then without the atmosphere, the water could not be sustained in liquid form and start to vaporize. We know there is still water on the surface, under the surface of Mars because we have seen it, but there is clearly no more water on the surface of Mars. But still, if you assume that for 1 billion years, these 3 planets had similar conditions, and knowing that life happened on Earth after 500 million years, well, you can also imagine that there must have been a beginning of life on Mars as well, and as well on Venus. So Venus is a bit difficult to land and to explore. Hopefully there will be in the future because the gravity is easy. You can easily go to Venus. What's difficult is to survive the condition on the surface, and you need new material to do that. But Mars, we can go. It's a bit more challenging to land on Mars, but it has been done, and it will be done in the future in a very, very, I think, massive way, hopefully. So Mars will be a planet that we shall explore in a complete sense. And then what we want to find out is whether there is some traces of life. But I mean traces of life, it doesn't mean it has to be alive. It just means that we can find something that can only be explained by the fact it has been alive. It's a bit like a fossil in a way. It can be a practical microscopic fossil. It could also be a geochemical fossil, knowing that the fact life is interfering with the natural geophysics of the surface of the rocks, you will find some anomaly on the rocks geophysics. To do that, unfortunately, we have to study that in great detail. It cannot happen with a robot right now, but it will happen later when the robot is picking up a lot of material right now, and it's picking up material in a fascinating area, which is the picture you have here. So you don't need to be an expert in fluid dynamics to understand this is a river. This is a river, which is a delta going into a lake here, and the robot is going up to this streamway, picking up sample that later will be brought back on Earth. So in about 10 to 15 years, we will bring back sample from Mars into Earth for extremely detailed study. I think it's a fascinating moment into human history. That will be the first ever time that we're going to bring back a piece of another planet. And that's momentum element here. And who knows what we're going to find out at that moment. Certainly possible some clue of the origin of life. Is this going to be life similar to Earth? Are we going to see nothing? Are we going to see some special chemistry that we're not expecting? Are we going to find out that life started on Mars and went on to Earth later on? I don't really know. But I think it's fascinating, and I really hope to experience that in the next 20 to 30 years. So Mars is there a bit. Of course, that will keep going and keep progressing. Now, the challenge here in all this is I'm talking about chemistry, I'm talking about planetary science, I'm talking about aeronautics, I'm talking about Earth science, studying planet Earth. I'm talking about astrophysics. I'm talking about developing new observatory in the future. It's a very, very comprehensive picture. In a sense, when people are asking me, oh, what do you mean by life? Could you define life? I keep telling them, what definition do you want? Do you want from an astrophysicist or do you want from a chemist? Because everyone we have a definition which is specific to the answer they can give. To have a picture for you, and you can imagine it's like a sculpture. So you have a 3D sculpture, and it has to be a 3D sculpture you don't really understand very well. So you cannot imagine what is behind. But when you look at a sculpture, you only look at one way of the sculpture. If you really want to understand the sculpture in a museum, what you have to do, you have to turn around the sculpture and to see, oh yeah, this is the complexity of the sculpture. Okay, and sculpture, imagine, is life. So we each of us, the chemists, the earth scientists, the geophysicists, and the astrophysicists, are looking at the sculpture with a different angle. We all see a different story. We all see something else about life. Altogether, it defines life. but individually, it only defines a specific angle of what we can see about life. And that's what we're doing. That's what we've started to do. And that's what I started to develop in Cambridge and ETH, which is what called a kind of a comprehensive development of these disciplines. We establish centers and try to put them together. So essentially, we have three problems. We have the chemistry, the astrophysics, and the story of the planets. There are three problems. They're connected. There's a lot of fascinating connections about specific problems. You can list a long answer about a specific problem that we're going to answer, each of us. And at one moment, we should be able to go to the middle. And the middle is life. So all of us is telling you something about life. No, the problem here is there is a lot of philosophical preconceptions. Of course, we only know one kind of life, which is on Earth. So we have to keep that in mind always, because it could be limitations. Because we're talking with different disciplines, everybody has his own definitions, jargon, and concepts. So we need to communicate a lot. So it's a lot about meeting to each other, communications, understanding each other to make sure that we, each of us find the clue that is useful to work together. And of course, we need to be able to work in a very focused way, knowing the expertise that you need to have as a chemist or as a geophysicist or as an astrophysicist, but also to understand what the other are doing. So it's at the same time, you have to be focused and to know exactly what you are aiming, because that's your expertise, but you have to be open. So we try to recreate a bit what has happened in the 17th and 18th century, where you had every scholar that would at least understand 2 or 3 topics before moving to a specific one of them. So we try to be a little bit global. We try to change the global teaching here. And of course, it has an interesting impact on universities and funding agency, because we're trying to tell them it's a very complex problem, so we have to find a new way to approach it. And we try to also demonstrate that this could be useful for other big problems, very complex problems that the society has to face. One of them is global warming. Global warming is a big problem because it's not only a problem of technology and atmospheric sciences, it's also a problem of sociology, it's also a problem of economics, it's also a problem of policy making. So altogether, you cannot solve the problem in one way. It has to go together globally. Another one is maybe AI. AI is also related to a very complex problem. It's engineering, making computers, but also software problem. It's also sociology impact, and it's also lawmaking aspects, and also the people responding to this. So we have this complexity of the world, and this fascinating knowledge we're building up. But in a way, we're still using definition of the science, which is based on the 100 years ago, the Victorian age of science, and we're still talking about chemistry and physics and biochemistry. And frankly, some of these topics I know go much beyond than that. So I'm trying to convey this message and to do talks, and I hope, I don't know, you have a different background, and I hope that I convince you that first that the topic is exciting. There is an amazing development in the future, and also we are gradually changing also the mental picture we're building in terms of the way we build up the knowledge of our society. Thank you very much. I have time for questions right now.
It seems there is
I can't hear it very well. I can't hear you very well. It's
okay, good.
The sound is very bad.
You have
Very bad.
So
you should use a microphone, I think. I don't hear very well.
Actually, can you see now? Can you hear?
I can't hear you.
So you better check it out.
这个是吧？
对。Can you hear now?
Yeah, it's much better now.
Okay, good, great. So now the questions.
Yes. Please do so.
You better come here. Professor Queloz, this is Wei Wang from NLC. I have 2 questions. Can you hear me now? Okay, perfect. So the first question is about your page 4. It's the mass period approach
Speak in the microphone. I can't hear you.
Okay. Now, how about now? How's it going? Hello?
No, can't hear you. It's very bad.
Hello?
Yeah.
Yeah, this is fine. Okay.
That's good now. Yeah.
Okay. So can you please go back to your slide 4? About the mass period plot.
Yeah.
I can see there's a vacancy in the long period Neptune mass range.
Yes. What do you mean the frequency? You mean the structure?
No, that's right. The distribution of planet in that area is quite small than the other area.
Yes. What is your question then?
Yeah. So whether this is what do you think is a real distribution or is caused by some observational bias?
Okay. So anything. Anything which is on the left side of this line is something we can detect. So the fact that there are a structure in the super Earth and Neptune, there's a lot of structure into this diagram, is interesting because it's telling you about the formation of the system. So I didn't want to talk too much about that, but there is two competing theory right now that is being developed. And depending exactly which way you form this planet, you may explain some of the blob and substructure you have. So yes, you're right, there are substructure there. So one way to form this planet is you form a planet like Neptune and you migrate in, and you kind of stop because there are other planet in the system that is dragging you, and then stop the formation of this planet. The fact that you form a Neptune that way has an implication on the structure of the Neptune. You expect to have it with a lot of water or CO2 because this is the way they're being formed there. The other way that people are thinking is you still form the Neptunes, something bigger, but because it goes so close to the stars, this planet is losing a lot of its atmosphere. So you remove the atmosphere, so you erode essentially the atmosphere. So you create something much more compact. So at the end, you end up with a bulk of planets which are within 5 to 10 Earth mass, some of them being more rocky because they have lost atmosphere, other that being more Neptune-like because they managed to survive and because the way they came up was very different. So the complexity of the formation of this planet is a hot topic right now, and we are a bit stacked because using only the mass and the size doesn't give you a complete picture. You need to understand what is in the atmosphere. So a lot of these planets are being targeted by the James Webb Space Telescope to get a detailed understanding what is the compositions of this atmosphere. So I hope that in the 5-10 years, we'll have enough of this planet with not only the mass and the size, but also the exact composition of the atmosphere to answer your questions. Where exactly is the origin of this planet? Of course, when you move down in mass, then we start losing the capability to detect them. And the more you approach this line that I had in my diagram, the more they become impossible to detect. So you need a new kind of developments, a new kind of technologies, and we're developing this machinery right now. There is a future space mission called Plato, will be launched in 2 years, and I'm developing a new kind of machinery called Terra hunting, which is the purpose to detect the smallest possible planet, some even like the Earth.
Okay. When in 1995, what are you feeling? Are you feeling very confident about this discovery? And are you expecting that one day you will get the Nobel Prize at that time?
I can't hear you.
Let me see. Okay. How about now?
Yeah, I can hear you well. Thank you.
So I have to do this. Okay. So my second question is that when you in 1995, when you discovered this planet, what was your feeling about this discovery? Are you feeling very confident about this discovery? And are you at that time thinking about one day you may get a Nobel Prize?
Okay, very good question. Thank you. Okay, so let me tell you the story of discovery so you will understand the kind of state of mind I was in. So I started the program in 1994, and essentially my supervisor, Michel Mayor, decided that nothing would happen at the beginning because all planets will take years to be detected. So he gave me the key of the machinery and told me, have fun and start the program. I will take my sabbatical and went to Hawaii. So I was left with the telescope for me, with the program to start, and I was very excited because I say, I start the program, it's exciting. And I wanted to do well because it was the end of my PhD, and I decided to follow a couple of stars in great detail to demonstrate the machine was working. And one of the stars was 51 Peg, and that star didn't make any sense because every time I was observing that stars, I ended up having a value that I would compute, which didn't make sense. It keeps changing every day. And I said, oh my God, there is a big problem in my software. So I thought really something was wrong in the machine or in the software. And I kind of panicked because I was at the end of my PhD and I said, my whole PhD doesn't worth anything because I cannot even compute something proper. And I get a bit obsessed by this. And I really wanted to understand where was the bug. It must have been a bug. And I battled for months without telling everybody because it would be a kind of at the end of my PhD, I felt I have to find out myself because that was my work, my software. I developed this machine, so I could not ask anybody around. I have to fix it. It should be easy to fix. And then the more I was working on that data, the more I realized that it must be real. There is no way it can be my software. And I did a lot of tests. And then there is a moment, there is a twist in my head. I say, it must be real. And I cannot explain this. I mean, I feel confident in what I'm doing. So if it's real, what is the consequences? So I then realized that it could not be an active star with spots because I know that star was not active. And I said, it must be a planet then. And then I started to hunt the planet. I tried to find the periodicity of the stars, and it took me some time to find the periodicity of the stars. And when I had a good solutions, I felt confident enough to send this information to my supervisor. And had a full phase, I had the mass, I had everything. I said, look, Michele was in Hawaii. I sent a fax at that time because the internet was not that powerful these days, telling him, look, Michele, I think I found a planet. And Michel has this very interesting answer. He said, yeah, maybe, but I don't think he believed me at that time because he was so bizarre. So he said, let's wait when I come back. He came back a couple of months later, and we worked together again with the data. And after some time, he realized I was right. He said, I don't see any other reason that being a planet. And we started to panic because we said, oh my God, this is a planet, really. And this is not a planet like no one had found. And it should be easy to be detected because it takes only 4 days to find this planet. So we worked hard on the paper, submitted the paper to Nature, and the Nature essentially said, it's not possible. It's impossible. We had a lot of trouble to get the paper being published. At some point, we said, we don't care. We're going to go public. And in November, we make the announcement in Florence meeting in 95, going public, saying, there's a paper in the process, and we don't want to wait. I think it's a huge stuff. We're absolutely sure this is real. And we made the announcement in the room in Florence, and I think very few people believed that stuff. They were very skeptical because at that moment, everybody was expecting a solar system like our own, and we came up with this very awkward planet. And as well, we have to realize that for 50 years, there has been a lot of fake announcement on that topic. So it was known to be minefield planet science. And when he made the announcement, I had my small moment of panic. And I say, oh my God, if I made a mistake somewhere, I'm dead. Because as a new scientist, I'm dead. So I got lucky in a sense that a couple of days later, one of the big competitors in the US had a telescope time and decided to debunk the announcement. He said, I will do some measurements and I will demonstrate it doesn't make any sense. And he did the measurements for a week and he sent us this beautiful email. He said, you guys, congratulations. I confirm everything you have done. And to me, that was a big relief there. But still, it was a big battle for the community because they thought it could have been many things. And it took a couple of years for the community to accept that they were this kind of bizarre planet. For me, as a young scientist, it was very difficult because for a couple of years, most of the people didn't believe me, and I didn't care. I was sure I was right. So I kept doing things. I say, I move forwards and I will do more things. I love science. I had this amazing experience. So I survived. And then in early 2000, when people started to realize it was real, people started to mention, oh, maybe that you will get one day the Nobel Prize. But, there's so much people that get told that. I say, well, maybe, but I just don't care. And I can tell you the day when I received the announcement in 2019, I could not believe it because there are so much great physics that's being done. I could not believe that discovery worth a Nobel Prize. But that's what it is. No, I have to live with that right now. I can't hear you. Sorry, I don't know why.
Okay.
Yeah,
I have to be very close to. Yeah,
I'm sorry.
Thank you very much.
It's bizarre.
Thank you very much for this story. They're telling a lot of truths. I can understand how what's the situation at that time, and I think this is a very good lesson to all the young audience today, for them to stick to their confidence, to stick to what they do, what they did. Thank you very much. And my last question is that do you have any interest or plan to visit China in the near future?
Oh, yes. China is a huge country. So yes, I do. I do start to go to China. It's a long trip to me, but I will certainly keep going to China. Definitely. I think I want to meet the community. The science in China is growing, and I think we need to get you together. We need to work together. There's still a lot of politics around that, but science is beautiful for that because we don't need all this. We're all speaking the same language, which is mathematics. So yes. This is really definitely, yes. I'm going actually to Shanghai in November, but I will keep going more and more often to China for sure. Yes, absolutely.
Okay, great. Thank you. I will leave time to other people. Thank you. Bye-bye.
All right. We have another question. Just wait a second.
Hi, Professor Queloz.
Hello.
I'm Jie Chen from NNOC. Thanks for your interesting and fascinating presentations. I have a skillful question. My question is: in one of your slides, you show us if we were in space, we can see the Earth and our atmosphere in different wavelengths. Can you explain why we can see the different height of the atmosphere in different wavelengths?
Yes. So what is the question?
You show us in one of your slides. You show us if we use the different wavelengths to see
yes.
the Earth and our atmosphere, and
yes.
the height, actually the thickness of the atmosphere is different.
Yes.
Can you explain why there is a different? Why the height is different?
Okay. So when you look in the infrared, in the thermal infrared, what you detect is the heat. You can use this infrared picture and you see the heat, the body of the heat. So you see where comes the heat of the Earth. So the heat of the Earth comes from the surface. So when you use an infrared detector, you don't see the atmosphere. You really see the heat of the Earth. That's why you see something smaller. When you work in a specific wavelength, when you have the ozone, what is going to happen is the wavelength is going to be absorbed by the ozone, because this is the molecule that will absorb the color. Because the ozone is sitting very high in the atmosphere, 50 kilometers, the light is being absorbed at 50 kilometers. So you cannot see below because it will become dark. You don't have light because it's absorbed. So this is why when you observe in the ozone band, you see a big Earth because you cannot see below because everything is absorbed by the ozone at 50 kilometers. It's like a cap.
Okay. Thank you. Hope to see you in China.
Sure, with pleasure.
Okay.
All right. Do we have other questions? 我们还有其他的问题吗？好的，你要不到这边来。 Just wait a second. Hello. Can you hear me?
Sure. Very well. Thank you.
I have two questions I want to ask you. First is from the page 4, the diagram. And if we have more samples and the technicals progressing, and we also have the same results, could we think our solar system is a bit unique in the universe? For that, in that diagram, I see that the Earth and the Venus and Jupiter is a bit different from other exoplanets we have found.
Yes, that's correct. Exactly. That's the main feature right now. So right now, we have not detected a planet like the Earth and Venus. I mean, in the same configurations. That's my message. So the reason why we have not done that, because we cannot, because of this limitation of the technology. So if you ask me, how likely do we have a system similar to other stars? My answer is, I don't know, because we cannot see them. But what I do know is already we're detecting a lot of planets on the stars. And the vast majority is different. So in a way, we use the opposite way to think about that. Because we have 80% of the star that have planets which are what we call super Earth and hot mini Neptunes, we know that they are already different from the solar system. What you have to realize is all of this super Earth and mini Neptune on short period, if you try to fit them into the solar system, they will be inside the orbit of Mercury. And there is no planet in the orbit of Mercury. So we know that the majority of the star have planets which are different. That's really the key message. But I don't know how many of the stars have a similar ones. But it has to be less because 80% are already different. So I am only left with 20%. So practically, this is a very open question. We may end up with only a few percent of the star that have a system like Earth and Venus. And then the big questions here will be to ask why? What happened in the formation of the system that prevent or protect, if you want to see that way, our planet to be moved inside and to end up being hot and impossible for life to strive. And that's one of these big questions that we will have to answer in the next 50 years.
Okay. And my second question is about page 5, the diagram. I saw that the density of Jupiter-like planets is not a straight line, but our Earth-like planets, the density is a straight line. Could I answer why the density of the Jupiter-like planets not a straight line?
Oh, okay. Because to compute the density, you have to combine the mass and the size. So if this is something which is a fixed density, it would be exactly an exact straight line. You're absolutely right, like a rocky planet. Now, in the case of Jupiter, these are gas. And the gas under pressure behave in a different way depending on the level of pressure. What is happening if you have a huge pressure on the gas, this is changing the physics of the gas. Most of the gas you use on Earth, and when you use in your bag, for example, it's called ideal gas, so perfect gas. So in a way, you have this direct relation between the pressure and the size of the gas. But when you can increase the pressure. In that case, the gas behaving more like a metal. It means the electrons start to mix together, and then they are in a state that we call degenerated, and in terms of space, in terms of physics, and then it's closer to a kind of a quantum state where they're all connected. So in a way, I give you the example. It's like a classroom with kids. So when the kids are in a classroom, they're well seated and they don't take much spaces because each of them have an organized seat and they have a chair and they have a table. Well, as soon as they go into outside the classroom because to play, they take a lot of space because they go random, they go everywhere. So going random everywhere, it's what we call an ideal gas or perfect gas. They take all the space they can. When the pressure rises, they become quantum numbers, and they need to be organized specifically, and they take much more space so that you can get a much denser structure. So you can get more mass without increasing the size. This is why when you increase the mass into the Jupiter and Saturn, you don't change the size very much, and you can keep increasing the mass. The size will not change because you're not random. You populate the quantum states, and then you can build them up. You can organize them like on a necklace, and they are taking the same amount of space. And even better, there is a moment when you reach the 40, 50 Jupiter mass, they take less space. They go down, the size goes down. It's very, very special. So it's a bit irrational, but that's related to the quantum state of the matter that we experience in this high density material at the center of Jupiter and Saturn. Good question.
So we have one question from online. I read it for him. So the student is asking, instead of just detecting exoplanet, will it make a difference to detect the moons of a giant exoplanet?
Okay, moons, right. So moons is predicted. When you form a planet like Jupiter, you form moons on Jupiter. Now, the moons orbiting the Earth is very special because it's much bigger. So for a rocky planet, you don't expect to find such a big moon. It's very special because it is the outcome of a result that is extreme that happened in the past. It may be very rare to end up with a moon like that. So we are not in a stage where we can detect easily moons, but there are a couple of attempts to find at least moons on giant planets. And it will happen. There is ways to do that using the transit. Finding moons on rocky planet, it's one step in the future. But certainly, it's a fascinating question. I mean, when you're having a kind of a rocky planet that will be similar to Earth, I think asking the question of moon is important because we know that moon may have played a very important role for life to leave the oceans because moon create tides, and tides help to trap life in a kind of mid-oceans, mid-surface situations, and life has to then strive and to survive, and then at some point get out of the ocean, get out of the oceans. Without tides, if you don't have moons, you don't have tides. It's not very sure that life would have left the oceans and evolved the way it has evolved. So I think it's a fascinating question. We don't have any right now, but we should look for moons, definitely. Very good question.
Right. Thank you. Do we have any more questions? Okay. All right. So we have still one more question.
Hi, Professor.
Hello.
Hello. Is an only
Oh, I can't hear you very well.
Hi.
Is
that
good.
Clear?
Yeah, it's good now.
Okay. So there's just one question. What is the most important, most crucial quality that you think that young scholars should have if they want to, keep doing the research in astronomy?
Interesting. Well, I keep telling that every researcher has shared the same way of behaving. They are extremely curious. When I say extremely, it's really extremely curious. So I think we're all curious. It's part of one of the, particularity of our species. And when we're young, we need to be curious to learn. Otherwise, if you're not curious, you don't learn. So you need to explore and to. But when becoming adult, we tend to lose a little bit the curiosity. And I think most of the top scientists, they manage to keep it. So my curiosity is still the same when I was young. I never get exhausted. So I always want to learn. I always want to know. So I think this is the first element. So you have to be curious and to be proud to be curious, because sometimes it's unusual. People keep telling you, oh, why are you so curious? So asking questions is very good. So a scientist is asking questions always, and asking questions and want to challenge things, understand things. That's the first one. The second one is, I think we have to be humble, because the universe is very complicated and we are very, very limited capabilities. So what we're doing is fascinating, because we have the mathematics, we're building equipment that can probe the interior of the atoms, that can probe the origin of the universe. It's fascinating, but still, we only know a fraction of the complexity of the universe. So we have to be curious, but humble, because it's difficult. If you have these two features, I think you will be successful into your work. So keep your curiosity, be humble in your work, keep doing good work, and things will happen, and you will be very, very excited and happy to do this.
Thank you, Professor. You know, it encouraged me a lot, because people keep saying that I ask you.
Yeah.
Thank you.
Be
Thank
curious.
You. Okay, I sure will be. Have a nice day. Thank you.
We have to today. Thank you, Professor. Again. I believe everyone has learned a lot from today's talk, and it's really a pleasure to have you with us today. I will finish the session now, and have a nice day.
Thank you very much. I hope you enjoy it, and hope to see you, some of you later, I'm pretty sure.
Hope we can see you in China someday.
Very, very happy. Yes, definitely.
Bye-bye. Bye-bye.
Bye-bye. Thank you.
谢谢大家，谢谢大家。